be surprised. So you want to introduce this again?
Oh, okay, yeah. So, okay, so starting here, we're gonna have a Google Colab notebook that goes over some examples of performing inference in Pyro. And we're gonna start with this mock data that we have on exams where we have paired data between midterm scores and final scores for each student. And this is what kind of looks like. So it's kind of just a blob that's somewhat Gaussian in a sense. And also you can notice like there's a slight trend between positive correlation between midterm scores and final scores. And we want to use Bayesian linear regression to model the association between the two. So with typical linear regression, it just looks like y equals wx plus b, basic like linear model that we're trying to fit the w and the b. But with Bayesian regression, we add this additional term called epsilon, which is some Gaussian noise. And then now when we're trying to do probabilistic inference, we also model the w and the b and the sigma square, which is parameterizing the noise as random variables that we're trying to learn the distributions of. And one thing to note is that since our data appears to be like homoscedastic, which just means that there's like constant noise that's independent of the input, this appears to be a good model since the noise that we have is just going to be constant across everything. So that might be a problem in certain cases, but not in this case. So here's the model for this Bayesian linear regression. So we'll see a lot of similar statements that we have in the presentation, where we have sample statements for all these latent random variables I'm having. And then we have a plate statement surrounding the students. So for every student, these are going to be conditionally independent from each other. So each of the scores is going to be represented by a function of the midterm score that they have, like that student had. And then also a function of some of these global parameters as well. So notice that something like final weight, which is kind of the slope between the midterm score and the final score, that's going to be global and affecting all the students in the same way. However, every student is going to be conditionally independent because they have their own source of like variation with their midterm score, and then whatever their realization of the noise is. And then I feed in the observation with the final scores here. Notice like in this case, the midterm scores is serving as like a parameter, whereas the final scores is serving as observation. And oh yeah, one thing to note is when you're using Pyro, the default is like 1.7, but I pinned 1.8 here, and it's because they recently added this function called render model, which allows you to get back like this LaTeX ticks-like model, visualizing whatever you had in your model function. So it's a really nice way to just kind of like sanity check whether your model code has the correct dependencies and like plates. And you can even add like render distributions equals true to generate just some text telling you how each random variable is distributed. Yeah.
There's a question in the chat about how to get access to the Colab notebook.
I have not sent it out yet, but I will send it to you probably right after this. And yeah, post it. It'll be on the website. Great. So yeah, so this is what it looks like, global random variables, and then pointing to this final score that's there's one for each student. So first, we're going to demonstrate how to perform inference with MCMC. And the reason for this is because you don't need a guide yet. You can just pop it in right into the MCMC kernel. So this is using a form of Metropolis Hastings called Hamiltonian Monte Carlo, using this like specific way to sample in a clever way called no U-turn sampler or NUTS. And basically, we can define how many warm-up steps do we want to take. So you didn't have warm-up steps because based on your initialization, you might be really far away from the true posterior. So to avoid having a bunch of noisy estimates from far away from where there's any mass on true posterior, you want to let it run for a little bit to eventually converge to the stationary distribution. And hopefully by then you're inside of the stationary distribution. And then you take some actual samples, which we define with num samples. So I'm not going to run this again because it takes like, I don't know, 40 seconds. And once I have these MCMC samples, I can plot them, like plot these histograms for each of the latent random variables that I have. So this is like the bias, the final weight, and the sigma. You can see they're all like pretty well concentrated, which is to be expected. Like we don't want to see any like weird bimodal distributions. But basically, like the image that I showed before, this is what it's doing. Like you can probably fit some kernel density estimate to this histogram and get an idea of what the true posterior distribution is. So once we have those, we can kind of we can plot out the estimates that we have for the latent random variables to just sanity check whether it's a good fit or not. So one thing I did here is randomly pick from the final weight and the final bias and just plot the linear regression. So the green one is referring to the mean of both the final weight and the bias. And you see it like passes straight through the middle, which is good. And the red lines are just random samples from both of the distributions. And you can see that it's still like pretty well concentrated around the data. So that's also good as well. We can also kind of get a sense of whether sigma has a good estimate or not. So this is not to be confused with like a confidence interval or like credible interval or anything, but rather I just took the mean of each of the distributions, including sigma this time, and plotted these error bars as plus or minus 2 times whatever the value of sigma is. So this should kind of encapsulate the randomness in the data. And in this case, we see it does capture a good amount of the data, and it's not like too big or too small. So we can say that sigma was also fit pretty well. So now we can try the same exact thing with stochastic variational inference. And in this case, I'm going to use the same exact model function as before, so I won't even rewrite it, but rather I'll just write a guide corresponding to it. So notice like we need to have the same exact function signature in order for a Pyro to work. So midterm scores, final scores, it's important that both of those arguments are there, even if you don't use our arguments inside of the guide function. And then kind of like I mentioned before, every single latent variable has its analogous parameter, variational parameter, and variational distribution. So like for final weight, we have this normal variational distribution, and we have a corresponding variational parameter for the mean and standard deviation that we're trying to learn. In addition to variational inference, you can mix in some map inference as well. So this is not like the best thing to do, but I just wanted to demonstrate that you can do it. So this dot delta is a degenerate distribution that just puts all of its probability mass on a single value. So what this ends up doing is resulting in the map estimate for the bias. So the prior that we defined in the model is still going to apply, but we're not going to have any variational distribution that we're trying to learn. Rather, we're just going to be learning a single estimate for the bias. And then now I'm going to perform inference with stochastic variational inference. So what that looks like is by having an optimizer very similar to if you train a neural net in PyTorch, and then you have this module. So SVI is also going to be, this is going to basically going to take in the model guide, the model function and the guide function, as well as your optimizer, and then start running like gradient descent over this elbow objective. So what that looks like is by doing some iterations and stepping every time. So this looks a lot like PyTorch neural net training code, if you've seen that before. And this is definitely like the aim of the Pyro people, to kind of make sure there's as little transition from PyTorch to Pyro as possible, so that the main things to understand is like how to define your probabilistic model and how to define your variational distribution, but everything else should kind of come naturally with regards to optimizing your distribution. So I just print out like the elbow value at each step. So in this case, this is like instead of maximizing it, this is like the negative version of it. So you want to minimize this instead. So this is just to follow like the classic idea of a loss function. So we see that it drops significantly and then kind of just like sticks around this area. So that implies that it's converged. And we can get an understanding of like what are the values of these variational parameters that Pyro learned. So we can do this by doing pyro.param and then having dot item afterwards. So one thing to notice is that I'm not even inside of anything Pyro, like remotely related to Pyro in terms of like the global environment that I'm working in. This is because Pyro has this very like unique thing of having a global parameter store where it stores the values of all these things it's optimizing over. And I don't know if I fully agree with this like, engineering decision, because this means that if you have like multiple models that you're training at a time and they have any conflict in the namespace, then it's going to just screw up one or the other when it comes to training. So this is the reason I had this additional line here, Pyro.clear param store. So this is generally a good rule of thumb to just run this before running any inference, so you don't screw up anything based on like the previous code that you ran. So this is how you can access it and just see the values that you learn. You can also get the posterior predictive distribution. So this is just kind of as if you're generating more observations from the distributions that you learned of the latent variables. So you learn a posterior distribution from the observed data that you have over the latent variables. Now that you have that, you can generate even more observations using like just the likelihood function that you define in the generative model. And this is what it looks like. You can see like Gaussian in a sense and centered around 0.6. And then we can do the same plotting that we had before, just to get a sense of like whether it fit well or not. And we see that it's very similar to before, which is good. So they came to a similar conclusion to each other, MCMC and SVI. Okay, so here I'm gonna go back to our presentation and talk about automatic differentiation BI. So one thing you might have noticed is that handwriting these guides is non-trivial. You have to pick these distributions manually. You have to make sure like everything plays nicely with each other. So you wish like there was a better way to do this automatically, and there is, and it's called automatic differentiation VI, also known as like ADVI. So basically what it does is uses tricks to adapt a single variational family to all the latent variables in your probabilistic model. So the way it does that is first by mapping any of the latent random variable distributions to the support of unconstrained real numbers. So say you have an exponential prior on a latent variable that you have, that's going to be strictly non-negative. However, if you want to use a Gaussian variational distribution with that, then it's going to bug out because KO divergence isn't well defined, where there's support for the variational distribution, but no support for the true posterior that you're trying to estimate. So what they do first is apply some transformation. So with the exponential, you can like take the log of it, and now it's going to cover all of the reals instead. And then now against the transformed version of this random variable, we can apply a Gaussian or like any variational family that you want without worrying about the support of the two distributions mismatching. So there's also like some additional tricks here to make sure things play nicely, but that's kind of the crux of the idea, to apply just like normal variational distributions to everything and like anything inside of the probabilistic model that you define. So like even if you put constraints on it, so like if something is constrained to be less than -2, they have a way to apply an invertible transformation to this, to the unconstrained real space and then back again for the purpose of like understanding what variational distribution you learned inside of the constrained space. So like this is an image of that on the right hand side. It's like some strictly positive distribution, but you can take a log of it and everything is going to be converted to the whole real space, and then you can do that in the reverse fashion as well. So in Pyro, this is referred to as Autoguides. So writing Autoguides are super easy. You literally just do like pyro.infer the autoguide dot whatever autoguide that you want to choose, and then plug in the model that you define, and then it'll just spit out a guide function. And then once you do that, you can pass it into like stochastic variational inference, just like we did before. You can also apply a combination of autoguides. So like if you don't want to use diagonal normal for every single latent variable that you have, you can combine them by using this like library of effect handlers in Pyro called Poutine, to specifically choose like which latent variables that you want to apply this autoguide to and which ones you want to apply a different one to. But the rule is just that like you can't have multiple autoguides for the same exact sample site, and it has to be covering every single sample site instead of your probabilistic model. So inside of the code, we basically can do the exact same thing here, where I literally do the same thing, except now I pass in this new guide that I defined with the auto guide, and everything else is exactly the same. And we see that it converges in the same way. And when we plot it, it looks like it's a good fit. So you can see like it's just so easily interchangeable and can be very helpful when it comes to iterating quickly over a probabilistic model without having to tinker with your guide every single time you make a change to the model function. All right, so just to wrap it up, I'm going to talk about like the general benefits to using Pyro specifically. It enjoys the benefits of PyTorch, which is super mature, constantly being improved, and caters to people who are already in the machine learning space. It has an intuitive high-level API, and it does a lot of the work for you. So like the stuff we're defining is almost one-to-one with, it's almost like you're writing like LaTeX code for your graphical model. It's very similar to that. So when it comes to basic models, it's really easy to do that. It also allows for scaling inference to large data sets by like allowing you to mini batch data in custom ways. So like that can be done with these custom keywords, keyword args into the pyro.plate function. You also have just-in-time compilation, which you might have noticed like I had in the MCMC code, but this just allows for the compilation of your code. So it speeds up by like being able to run machine code directly rather than having to interpret Python the entire time. So this is useful when you're like training for long periods of time. And typically in Pyro, it's just a one-liner to add this like feature to your code. And then caveats to using Pyro is that it's still relatively young since it's like open source in 2017. They're only on like version 1.8. So this means it can be pretty brittle when it comes to implementing more complex models. So if you go beyond just having like a very basic like BayesNet kind of thing, then you have to start digging into like the dark depths of the Pyro API. So that was what I mentioned before called Poutine. This is what Pyro is built on top of. It's kind of like a wrapper using a bunch of these functions inside of the Poutine library. That's just a submodule of the Pyro library. And this is kind of like where the magic happens, where the black box stuff like opens up. But the documentation is like definitely more limited than the Pyro level API. And it can get pretty complicated pretty fast. So that's definitely one con of trying to work with Pyro. Debugging can be pretty difficult due to like the same black box idea that's trying to make the high level API super simple. So when it works, but when it goes wrong, it can be very painful. And I speak from personal experience. And this Pyro also focuses more on variational inference. This is kind of makes sense because having like all that deep ML infrastructure operates better with variational inference than it does with the MCMC methods. So support for MCMC is lacking, although like the implementation is there and you can use it. And lastly, the alternatives to Pyro that exist out there. So the big one is Stan. This is like probably one of the oldest probabilistic programming languages there are, and it caters more to like statisticians. And it's in its own Stan language as well, but it does interface a lot, with other languages like Python, Julia, R, in case you want to use it with like other libraries. There's also a TensorFlow probability, which is built on TensorFlow, as you may have guessed. This recently kind of like merged with Edward, which is the following one that I mentioned, which was also built on TensorFlow, but Edward 2 is now included as a submodule of TensorFlow probability. So it's kind of just like one good pick if you want to make probabilistic models on TensorFlow specifically. And then lastly, there's PyMC, which is also a pretty old package. It was built on Theano, which is another deep learning like auto differentiation library that's no longer going to be maintained after like a year. So this is like one reason a lot of people are moving away from it. But otherwise, it's like pretty mature and like feature rich. So it's still a good choice if you don't care about like the improvements to the underlying auto differentiation and like machine learning library. yeah, so that's all I have. Thanks for listening. And if you have any questions, feel free to ask.
I think we have the room until 15 after, so feel free to ask as many questions as you want.
Yeah.
How widely used Pyro?
Oh, what'd you say?
How widely used?
Oh, how widely it uses it? I'm not actually sure. Well, yeah, I'm not sure like how widely it's used in like industry production code, but I know in research it's used like in a bunch of different places here and there. For example, at least like in the package that we're working on, SCVI tools, you can operate, you can like build models in Pyro rather than PyTorch. We have like LDA implemented in Pyro and also like ScanVI, which is another method that we have implemented in the SCVI tool suite. Also seeing like implementations of like factor analysis from like this bioinformatics lab in Harvard. So it is like getting more popular in the bioinformatics community specifically. It's probably related to it being part of the Broad Institute now. So I think they're trying to push on that front. But I think more generally, I'm not really sure like how it compares to. I'm pretty sure like Stan is probably the most widely used just for like legacy reasons. Also, it's like still pretty usable. But yeah, Pyro is still pretty young, so I can't imagine that it's widely used.
And now they have a non-Pyro, which is built on
JAX. Yeah.
it's like even supposed to be simpler than this.
Yeah. So JAX is like even more bare bones, like auto differentiation library, and the Pyro guys have a version called NumPyro that's built on that instead. Yeah. I didn't hear the full question. Did you hear the question? Oh, yeah. So I think the question was just like, can we add more parameters to our models or like covariates in order to improve like the estimation of our model? Is that the question? Kind of. Yeah. Okay. So definitely yes. Like I think the fact that it's so easy to build a probabilistic model and iterate on top of it means that you can extend how much you're modeling inside of any given situation. So for example, with like the midterm scores, one thing you can do is have the midterm scores also distributed as a random variable, and then have maybe like another latent variable that's specific to each student, which is like their true ability or like true like motivation or something. And you can have any other covariates as well, like how busy they are, like what other classes they're taking. So kind of the sky's the limit when it comes to probabilistic modeling. Everything is going to be like inaccurate when it comes to complex data sets, but you can try to capture as much of the variation as possible by adding covariates that make sense. And that's super easy to do with Pyro, I would say. Yeah.
Pyro handle like undirected basic graphical models.
Probabilistic graphical models.
Undirected models. I mean, basically, usual examples for making network where you have like some definition for like conditional independence or something like just like find all those like directed arrows. But what if the model is undirected?
Undirected.
Oh, undirected. Oh yeah, that's a good question. I don't know. I don't think so. Yeah, I don't think so.
Are there classes of models that are undirected that you can do Bayesian inference off of?
I mean, like, I guess traditional inference how we use like in undirected models for sometimes, like Ising model basically.
The what model?
Ising.
I think it will help me like trying to use data message for those models as well, but I don't know like whether it is implemented in probably not. You want the syntax.
Yeah.
That the condition, like a lot of the variable inference stuff relies on like having like a posterior distribution that's gonna be relatively simple because you can rely on conditional dependencies. But if it's undirected, you'll have a lot of other. You won't have as many conditional independent variables, right?
Yeah.
It depends on the configuration of the network. You wanna like only like neighbors with terms. I don't know if you know that. Definitely like that's the problem.
That's
Yeah.
super cool.
Beyond that, like I feel like with the basic syntax at least, it's probably not possible to define something like that. But yeah, it makes me wonder whether like with the poutine library, like if you do it directly, if there's a way to possibly define something like that. Yeah, I mean, yeah, I could probably ask some of the Pyro guys.
And Pyro guys have a really good Slack. You can just join and ask them questions and they answer everything. Since they're
For them.
Yeah.
I have two questions.
Oh yeah. Okay.
First one is, how well does the Autodiff library work in your experience?
In terms of like getting nans or just like going out of control, or
Yeah, like does it actually fit more complicated distributions? Well,
yeah, I think it works pretty well. Although like I've had some trouble with certain distributions that aren't like reparameterizable, like Dirichlet.
Yeah.
So I think there's still like kinks and stuff in there. But in general, it works pretty well, I'd
You
say.
need the Autoguides.
that's a
Oh, the Autoguides.
Yeah.
Oh, I
that's
see.
a-
Oh, the Autoguides. Oh. Oh, I haven't used them that much, so can't say. In terms of usability, or like just trying it out, it's super easy.
I see. And the second question I had is, do you have like general advice that you can offer people on how to come up with graphical models for their data?
I don't know. I feel like if you're going for something simple, then you kind of just look for like covariates that will make sense and how they relate to the rest of the latent variables that you have and how it ties in with your data. But when it comes to like more complex stuff, so there's a lot of different complicated things that can be represented as a graphical model. Yeah, I honestly don't know like how they come up with that from scratch, but yeah, it can get pretty complicated. But yeah, I don't know. What is the most complicated thing that you can represent or like that Pyro has implemented?
Well, I think this it's probably fair what you said. That's what I would have said too. It's just really complicated. It
Yeah.
probably pays a lot to work with an expert who knows how data is generated, all the noise models.
Right,
So
yeah.
like a good example perhaps in our field is how do you model the observed amount of RNA of a particular gene in the cell?
Mhm.
And if you look at the SCBI model, it's pretty complicated.
Yeah.
And yeah, you have to work with a biologist or someone that's.
Yeah.
Yeah.
I think definitely when it comes to biological data, it's like a prime example of how the distributions are not obvious. Like you're not just gonna throw like Gaussians everywhere. Instead, you use something that makes more sense given like the sampling model of like picking RNA out of the transcripts of the cell and stuff like that. Yeah, Richard, you have a question?
I could actually probably just add on for it.
Okay, yeah, sure.
Cool.
All right.
Any other questions? All right,